Hello everyone and welcome to my channel. This is an educational channel. We take a look and do deep dives on cosmologies and theories of everything and such like. Things that I think could improve your life if you knew about them, but they're terribly obscure and suppressed, and so you probably don't. Today is our 444th video on the reciprocal system of theory from one Dewey B. Larson. Mr. Larson proposed his two fundamental postulates in 1959, just two sentences about how he believed the universe operated, and then he, through a process of deduction, he elaborated those postulates into a theoretical universe, a universe that was just, in his head. This is how the universe would look if my postulates were correct. And then he compared his theoretical universe with the measured universe of the scientists. We're looking at one of his books called Basic Properties of Matter, where he compares his theoretical universe of chemistry with the chemists who had done experiments in their laboratories and compiled the basic properties of matter in their tables, scientific tables, and things like the melting point and the specific heat and the interatomic distance and the compressibility. Larson was able to derive equations for all of these. And then he plugged his the numbers into the equations, and then gave values for the various properties and compared his results with the results of the scientists. We're looking at chapter 5 in this book that's called Heat, and it is a very difficult chapter. And he gets into a lot of stuff that's very detailed and probably, for a beginner, it's probably a little bit too much. It's too much for me, and I'm not a beginner. But it just gives you an idea how he thinks about these things and everything. So let's just introduce the reciprocal system. Larson's two postulates. The first postulate is that the universe is made entirely, or is composed entirely, of one component: motion, existing in 3 dimensions, in discrete units, and with 2 reciprocal aspects, space and time. And then the second postulate is that the universe conforms to the relations of ordinary commutative mathematics. Its primary magnitudes are absolute, and its geometry is Euclidean. Okay, so Larson is called the reciprocal system, also called the universe of motion. The universe is made out of motion. Not matter, not energy, but motion. And Larson is referring specifically to what he calls a scalar motion, which is a more generalized kind of motion than the vectorial motion that we're accustomed to. A scalar motion is a motion that has a magnitude but has no specific direction. You can envision this by using a balloon. You blow up the balloon, all the dots, a balloon that you put dots on. And if you blow up the balloon, all the dots will be moving away from each other, but they won't be moving in any specific direction. Every dot will be moving away from every other dot. And in fact, every location on the surface of that balloon will be moving away from every other location. So every dot is moving in every direction. And that is a scalar motion. It's really just in or out. Is the balloon going in or out? The outward motion, Larson calls the progression. The inward motion, he calls gravitation. And so he uses that motion as his source to create everything else. Now, the other part, another part in the postulates, is that motion, for Larson, is the relationship between space and time. This may sound absurd. That means that motion, that space and time are reciprocals of one another. Basically, motion is a fraction with space or time as the numerator and time or space as the denominator. And, Larson admitted that he felt that, space as the reciprocal of time is kind of an absurd idea. But then he looked at speed. Speed is our most basic form of motion. The bike is moving 10 miles an hour. 10 miles of space in 1 hour of time. Speed is space over time. And if you double the speed and you say the bike is now moving 20 miles per hour, you can equivalently say the bike is now moving 10 miles per half hour. They're both the same. You can either multiply the space or divide the time. That evinces a reciprocal relationship. So there is a reciprocal relationship between space and time in speed. Larson extrapolates that and applies it to all forms of motion. So he says that really every kind of scientific phenomenon is a form of motion. Matter, energy, pressure, temperature, power, acceleration, momentum. These are all fractions with space or time as the numerator and time or space as the denominator. Now, space or time, as it says in postulates, space, time, and motion come in 3 dimensions. So you can have 3 dimensions of time, space, or in that fraction. And really, you can go up to 6 because, say, for example, you have density. Density is matter per volume. And so density, matter, it turns out to be time to the 3rd power over space to the 3rd power. And then volume is space to the 3rd power. So density is time to the 3rd power over space to the 6th power. Now, say you've got that expanding balloon, say you've got the contracting balloon. There's the motion is just in or out, in this case in, but there's no specific direction. But say you want to arbitrarily define a reference point, and you say, okay, this particular dot is not moving. And once you do that, you've kind of like stopped the universe, stopped that scalar motion, and you're now able to make determinations as to the direction of all of the other dots. And it will appear as if there's there are force fields, that each one of the other dots is being attracted to the reference dot. Larson calls this an as-if force, but this is also what you would call the spatial reference system. So the spatial reference system, the one that we normally reside in or observe, is 3 dimensions of space in a still frame, like X, Y, Z coordinates, along with progressing or flowing or scalar time. Time is moving forward, always moving forward, getting later and later and later. But space is now vectorial. Okay, so you've basically stopped the universe in space to make these measurements, and so you end up with this 3 dimensions of space, 1 dimension, or you have progressing time. The spatial reference system. Okay, now you also, in order to have, that is 1 dimension of motion. Okay, space and time have 3 dimensions. That's 3 dimensions of space, but those 3 dimensions of space just only encompass 1 dimension of motion. And then you can have the inverse of this as well. In a different environment in the universe, you could have 3-dimensional time, in a still frame if you abstract the time instead of the space, and you measure the space, or you measure the time instead of the space, then you can have 3 dimensions of time in a still frame and progressing space. Space is always getting later and later and later. So this is what Larson calls the temporal reference system. And this also is 3 dimensions of time, but 3 dimensions of time encompass only 1 dimension of motion. So really you have 3 dimensions of motion. You have the spatial reference system, you have the temporal reference system, and then you have this scalar reference system, just this progression and or gravitation of just space and time without any stoppage. So those are 3 dimensions of motion. Now the other part is the discrete unit postulate. Time, space, and motion come only in discrete units. You have to have a full unit of space before you have space, for example. And if you have exactly 1 unit of space in 1 unit of time, again, remembering that space over time equals motion, space over time equals speed, more specifically, then 1 unit of space in 1 unit of time is 1 unit of speed. Larson calls that unit speed. And unit speed is also known as the speed of light. So this speed of light is the background motion of this universe of motion. If you are going to accept a universe of motion, you have to be able to accept motion without anything moving. Motion precedes the thing that's moving. And this is the motion that precedes everything. This is omnipresent and eternal in this universe, is the outward motion at the speed of light in all directions. Okay, so a scalar motion, 1 unit of space in 1 unit of time. And that is continual at every location at all times in this universe. So that is the source, the 0 point, the null point, the origin, the ether. And then the universe is constructed from basically reversing those sources. So that's where you kind of get photons, and then subatomic particles and atoms, and then compounds, and then aggregates, all come from that original outward motion at the speed of light in all directions. Okay, and then so we have this also creates, this is the midpoint. So this creates a half the universe is moving faster than the speed of light, half is moving slower than the speed of light. Larson refers to these as the cosmic sector and the material sector. In the material sector, you have coordinate space and clock time, or the spatial reference system. In the cosmic sector, you have coordinate time and clock space, or the temporal reference system. These are reciprocals of one another. When you cross that boundary, you have to invert the rules or switch the functions of space and time there. Now, each one of these sectors, material and cosmic, have a subregion that it has to do with the discrete unit postulate also, the unit of space in the material sector and the unit of time in the cosmic sector. When you have atoms and molecules and so on that are interacting in less than 1 unit of space, which is about 1/500,000th of an inch, then you don't have space because it's less than 1 unit. If you don't have a full unit, you don't have anything. So if you don't have space, then you only have time. So Larson calls this the time region. This is the region of interaction of material, atoms, and particles and compounds. And when you cross that boundary to move into the time region, you invert the roles of the progression and gravitation. So now the progression is moving inward and gravitation is moving outward. And the same thing occurs in the cosmic sector, except with time instead of space. In less than 1 unit of time, you have only the space, and Larson calls that the space region. And this is the region of interaction of cosmic atoms and cosmic molecules, which we know of as mesons or antiparticles, antimatter. Okay, we're going to start reading here from Larson on heat. This is about the 5th episode that we've done, and my recommendation is just follow along the best you can, glean a few things, mainly about how he's thinking about this, how he's approaching it. You might not get all the details, especially if you don't have a science background, which I don't. And I don't either, I'll just say. And you know, you're just trying, this is a detective job, basically. We're just trying to understand as much as we can and put it all together at a later time. I would recommend not dismissing anything out of hand because it's different than what you're accustomed to, but just kind of take it in and marinate on it. Don't accept it or reject it, but just take it in. And then later, when you've had the full picture presented to you, then you can kind of weigh it and discern. Okay, on first consideration, this temperature unit. Okay, Larson derived the temperature unit in the last episode. This is the unit of heat. Heat comes about as a result of the gravitational forces or the rotational forces in the time region, more or less, I guess, vibrating, motion. And when you have the time region, there's an equilibrium that's established in the time region between where the force of gravitation and the force of the progression are equal. This is an equilibrium distance between the molecules or the atoms, and then that equilibrium distance can be affected by the temperature or the pressure or both. And he derived equations like energy equals pressure over volume and such like. Okay, on first consideration, this temperature unit, so the natural unit of temperature, he determines the natural unit of everything, because that you can do this in the reciprocal system where you have the unit, everything is in space or time units. So if you say energy in the reciprocal system is time over space, so all you do to figure out the unit of energy, I would think, and I'm not sure that Larson actually does this, but you would use the unit of time, which is 1.52 times 10 to the minus 16 seconds, and then you would divide it by the unit of space, which is 4.56 times 10 to the minus 8 meters. I think Larson alters that slightly for various reasons, and I'm not sure exactly why. I would think that it would be simpler to do it that way. I'm going to try to figure that out a little bit better here in the future, but that's where so he derives this temperature unit, which is actually like 7 trillion degrees is the temperature unit for the time or for the time-space region, the region outside the time region. And then he alters it to less than that for being partially in the time region. These are really the states of matter. Solid is 3 dimensions in the time region. A liquid is 2 dimensions in the time region, or 1 dimension out of the time region. A gas is all 3 dimensions outside of the time region. And I think a vapor is really 2 dimensions outside the time region. On first consideration, this temperature unit may seem incredibly large, as it is far above any observable temperature, and also much in excess of current estimates of the temperatures in the interiors of the stars, which according to our theoretical findings can be expected to approach the temperature unit. I'd like to understand what his theory is there, but he doesn't elaborate. However, an indication of its validity can be obtained by comparison with the unit of pressure, inasmuch as the temperature and pressure are both relatively simple physical quantities with similar but opposite effects on most physical properties, and should therefore have units of comparable magnitude. The conventional units, the degree Kelvin and the gram per cubic centimeter, have been derived from measurements of the properties of water and are therefore approximately the same size. Thus, the ratio of natural to conventional units should be nearly the same in temperature as in pressure. The value of the temperature unit just calculated, which is for the condensed states, I guess 3.6 times 10 to the 9, 3.6 billion degrees Kelvin, conforms to this theoretical requirement, as the natural unit of pressure derived is 5.38 billion grams per centimeter squared. It says cubed here, but pressure is grams per centimeter squared. Well, no. Pressure is energy per volume, and it is force per area. So I don't know why we'd use a cubic centimeter there. Anyway, except insofar as it, because a gram is time to the third power or space to the third power. That would seem like that would be the density. It would need to be force per, or energy. Anyway, I think that's a typo, or something's wrong there. Except insofar as it enters into the determination of the value of the gas constant, the natural unit of temperature defined for the gaseous state plays no significant role in terrestrial phenomena. Here, the unit with which we are primarily concerned is that applicable to the condensed states, liquid and solid. Just as the gaseous unit is related to the maximum temperature of the gaseous state, the lower unit is related to the maximum temperature of the liquid state. So this would be like the boiling point or the critical point, one of the two. This is the temperature level at which the unit molecule escapes from the time region in one dimension of space. I thought that would be the melting point, that where it escapes in one dimension of space. Okay. The motion in this low energy range takes place in only one scalar dimension. We therefore reduce the three-dimensional unit, 3.6 billion Kelvin, to the one-dimensional basis and divide it by 3 because of the restriction to one dimension of space. Okay, so you have to take the cube root of this number and then divide it by 3 in addition to that, of 3.6 billion. So, you know, you're talking about, 1.5 thousand, and then you divide that by 3, so like 500. So because of this restriction to one dimension of space, the natural unit applicable to the condensed states is 1/3 times 3.6 times 10 to the 9 to the 1/3 degrees Kelvin equals 510.8 degrees Kelvin. The magnitude of this unit, and again, the Kelvin scale goes down to two. It's an absolute scale. It starts at zero, at absolute zero, and so 510.8 K is the same as 237 degrees Celsius. So that's you know, the boiling point is 100 degrees Celsius. And so that would be, you know, 237 degrees Celsius is, you know, on the order of, you know, 450, 500 degrees Fahrenheit. The magnitude of this unit was evaluated empirically in the course of a study of liquid volume carried out prior to the publication of The Structure of the Physical Universe in 1959. The value derived at that time was 510.2, and this value was used in a series of articles on the liquid state that described the calculation of the numerical values of various liquid properties, including volume, viscosity, surface tension, and the critical constants. Both the 510.2 liquid unit and the gaseous unit were listed in the 1959 publication, but the value of the gaseous unit given there was subsequently increased by a factor of 2 as a result of a review of the original derivation. Since the basic linear vibrations, or photons, of the atom are rotated through all dimensions, they have active components in the dimensions of any thermal motion, whatever that dimension may be, just as they have similar components parallel to the rotationally distributed motions. As we found in our examination of the effect on the rotational situation, this basic vibrational component amounts to 2/9 of the primary magnitude. So that 2/9 is the photon. That's 2 photons at the core of every atom is 2 photons, and each one of them occupies 1/9 of a rotational magnitude of the primary magnitude of the atomic rotation. Because the thermal motion is in equivalent space, because the thermal motion is in time, also known as equivalent space, because we don't see time, we only see space because we're anchored to the spatial reference system. But so when something occurs in the time region, we do not see it in time. We see the inverse of it in space, because space and time are reciprocals. Then we also have to reduce that by a certain amount that's getting lost in the translation when we were looking into a different region or sector of the universe. And we also see equivalent space as a second power entity. So these are rules that you kind of have to know, not just for this application, but for all fields. Again, the reciprocal system, it's a system of theory. So you can learn this theory of chemistry, and it seems incredibly complicated. But the reason why it's so important is because if you learn it for chemistry, then you've pretty much learned it for all other subjects too. You're not learning, one set of jargon for chemistry and then another set of jargon for biology and then another set for economics and another set for history. This is an integrated system. So once you understand how it works in one field, you can apply that field, that same knowledge, to apply it to another field. Believe me, otherwise I wouldn't be going through this process of trying to learn this unless I believed that it was integratable into every subject. Okay, so because the thermal motion is in time or equivalent space, its scalar direction is not fixed relative to that of the vibrational component. And that's because the direction in time is not related to the direction in space. This vibrational component will therefore either supplement or oppose the thermal specific heat. I guess, and that's kind of determined by chance. The net specific heat, the measured value, is the algebraic sum of the two. This vibrational component does not change the linear vibration of the specific heat to the temperature, but it does alter the 0 point, as indicated in figure 2, which we don't see here. In this diagram, the line OB is the specific heat curve derived from equation 5-7 that he introduced yesterday. Assuming a constant value of n and a 0 initial level, if the scalar direction of the vibrational component is opposite to that of the thermal motion, the initial level is positive. That is, a certain amount of heat must be supplied to neutralize the vibrational energy before there is any rise in temperature. In this case, the specific heat follows the line AA parallel to OB above it. If the scalar direction of the vibrational component is the same as that of the thermal motion, the initial level is negative, and the specific heat follows the line CC, likewise parallel to OB but below it. So the photon is either going to add to this amount of a specific heat, or it's going to lower it. But the line is going to be parallel. Here there is an effective temperature due to the vibrational energy before any thermal motion takes place. And again, this specific heat curve is going to be segmented, just like the curve for the compressibility. Line segments connected by curves, because at certain points there are going to be certain inflection points. And we'll look into that as we go along in this chapter. Now, just don't get discouraged because you don't understand this. Just try to hang on and get what you can get out of it and just kind of get his perspective. I'm trying to present this stuff because it's not out there on the internet. And, you know, if you are really studious, you can take what I'm giving you and you can run with it. If you're not so studious, then you might want to wait for me to write up this. I'm going to be pretty much trying to roll this out on a red carpet for people, but it's going to take a little while for me to kind of put my notes together. So that's kind of where I'm at with it. And thanks for tuning in today, and have a great day.